Let's try to multiply some matrices. We're given two matrices here. Matrix C has size 3 by 1. So let's write that off to the side here. That's 3 by 1. And remember, when you're multiplying matrices, we want to see if this multiplication is even defined in the first place. So let's check matrix D. The size of matrix D is 1 by 3. One row with 3 columns. So remember, the first thing you want to do is check to see if these match. If the number of columns in matrix C matches with the number of rows in matrix D, then we say multiplication is defined. So if it's defined, then that means C times D really does exist. Now the second part is very interesting. If you take the outside numbers, you have this outside 3 and that outside 3 right here, this will actually tell you the size of C times D. So C times D has the size of 3 by 3. So that will tell you that you actually will have 9 entries. Now, how do we get C times D? First thing you probably want to do is write matrix C, negative 7, 0, 3 in the column position, and then write matrix D next to it. Remember, there's an invisible dot in between these matrices. So what is in the 1, 1 entry of matrix C times D? Let's find out. It turns out it is simply negative 7 times negative 5. So how do we get the 1, 2 entry? Well, we need the first row in matrix C, and then we want to multiply to the second column of matrix D. In this case, we have negative 7, and then times 2. And if we do the 1, 3 position, we'll also have negative 7, but it will be multiplied to negative 6. Now this is supposed to look like a square matrix, right? Because it is size 3 by 3. So I'll try my best to draw a square. It's going to be slightly off. We could actually go to the next row, and we want to find the entry 2, 1 position, which means the second row and first column. So we need the second row of matrix C, and we need the first column of matrix D. So in this case, it will be negative 5. Okay, so there's definitely a pattern going on. Once you get the hang of this, it's not so bad. So in order to get the 2, 2 position of the matrix C times D, we need the second row of matrix C and then the second column of matrix D. The second column would have a 2. For the 2, 3 entry, we need the second row of matrix C and the third column of matrix D. In this case, it's going to be 0 times negative 6. And so we could definitely figure out what's needed in the 3-1 entry, 3-2 entry, and a 3-3 entry. So in the 3-1 entry, we need the third row of matrix C, and then we need the first column of matrix D. Well, that leaves us with -7 times -5. Oh, I'm sorry. I said the third row of matrix C. That would have to be a 3. What about the 3-2 position? Then we need the third row in matrix C and the second column in matrix D. And so the second column in matrix D has a 2. We know by now the third row in matrix C has a 3. How about the third column in matrix D? We would have -6. Well, let's simplify that. What does our square matrix of C times D really look like? I'm sure you guys know how to multiply. So there you go. That's matrix C times D. What about D times C? Why don't we check? Part B, if you write D times C, and we know that size D is 1 by 3, and size C, or matrix C, has size 3 by 1. So, once again, the columns of the first matrix does match with the rows of the second matrix. So if these match, then multiplication is defined. Now, what is its output? D times C is actually just a 1 by 1 matrix. Let's figure out what it is. So let's write D times E is now equal to -5 to -6. And this time matrix C is in the column position -7, 0, 3. So what would that 1 by 1 matrix look like? It'll simply be -5 times -7, add 2 times 0, add -6 times 3. Simplifying that, we get 35 minus 18, so 17. And there you go. Both C times D and D times C are defined, but they look completely different. C times D has size 3 by 3, and D times C only has the size 1 by 1.